This is really exciting for me to be able to speak with you today. I started collecting minerals back in the same period when your society was founded back in the 1960s. Living in northern New Jersey and being just a short drive to Patterson and the famed quarries there and Franklin and Ringwood and lots of other places, and collecting micromounts, which really in a major way is what got me most interested in mineralogy. I decided to go to MIT in part because I had collected some specimens that I just didn't understand and I wanted to learn more. And hey, I never looked back. And I've never worked a day in my life because I get to work with what we're all passionate about, and that's minerals. And I want to remind you the importance of mineralogy. I mean, I think we all know this, but minerals provide all the essential raw materials, technology in agriculture, but also for life. We depend on minerals. And they're what preserve a record of planetary history, including biological evolution. If we want to understand places like Mars and the moon, we got to study the minerals. Minerals have laid an absolute foundation for all sorts of advances in chemistry and physics. The discovery of the periodic table, Bragg's X-ray diffraction, and many, many other important discoveries. Nobel Prizes have been awarded to a number of people who studied minerals. But I think we all agree that the importance of mineralogy lies as much as anything in their just diversity and their beauty and the astonishing things we can see when we look down a microscope at these beautiful, beautiful objects. The point I want to make today, though, is expanding on that mineral specimens are information rich. Every single mineral specimen you've collected is a time capsule. It's just waiting to be opened to tell its story. And that's what I want to talk about today. What I want to do is I want to review the official International Mineralogical Association classification system, which is based on chemistry and physics. I want to propose a complementary system of classification that's based on information, and it's called an evolutionary system. You'll see what I mean. And in the process, I'm going to introduce opportunities that are offered by this incredible new age that's opening up, mineral informatics. For example, in exploring how Earth and life have co-evolved. So think about it. What are the objectives of a mineral classification system? Why do we classify things? And of course, the first most basic thing is we want to be able to talk to each other. So we organize natural objects so we can be unambiguous about describing them. And I can say, hey, I found this fabulous specimen of I don't know, sphalerite, and you understand what I'm talking about. We can talk about it in that way. But in addition, a classification system ideally plays some kind of central role in discovery, scientific discovery, and in the articulation of scientific theories. And I think because of that, it's perfectly okay to have multiple valid classification schemes, each one of which addresses a different theory or aspect of nature. So the IMA classification system, the one we all use, the mineral is defined as a natural occurring solid. It has its idealized end member composition like quartz is SiO2. It has its idealized structure. So you have the quartz structure. And all of them, I looked today, it's like 5,780 approved IMA mineral species. They all have a unique combination of idealized chemistry and idealized structure. This goes back to 1850 in the third edition of Dana's system of mineralogy, in which he used chemical and structural aspects to define each of the mineral species, the 1,000 or so that he described in that 1850 edition. So here we have a way of classifying minerals that's incredibly elegant. And indeed, part of the reason it's elegant is because it uses the absolute minimum amount of information to describe a species. And I mean information in the technical sense of the bits of information. So you have an ideal crystal structure and an ideal composition. That's the minimum information to describe that specimen of quartz, is distinct from calcite or pyrite or something else. But I argue that if we want to understand Earth, its history, the origin of life and its evolution, then we need a different classification system that incorporates changes of minerals through deep time. Time needs to be a variable. Okay, so why would I propose a different classification system, this evolutionary system? And as I said, the first reason is because the IMA system doesn't incorporate time, but Earth has changed incredibly dramatically over more than 4.5 and the mineralogy has changed as a result. And we see these sequences of change because planets are dynamic systems. The histories are recorded in minerals, and this evolutionary system that we're talking about has a potential to inform theories of planetary origins and evolution. There's a second reason. This is a little bit more abstract, but I think it's really kind of cool also. There is an old idea in philosophy, it goes back to Aristotle and even before, something called natural kinds. When you're classifying things, a natural kind is supposed to represent a genuine division in nature. That is a group that's independent of our kinds of conventions, our interests, our actions. And the idea that many philosophers of science talk about is the periodic table, where each of these chemical elements is defined by an integral number of protons. Carbon is element 6. It has 6 protons in the nucleus. It is therefore different from any other chemical element. It is a natural kind. It's a genuine division. Carbon is different from boron. It's different from nitrogen. Now, the idealized IMA species cannot possibly be natural kinds because they're fictional. There's no such thing as pure SiO2. There's no such thing as the idealized quartz structure. But a new system that incorporates that kind of messy history, all the information that mineral specimens contain, could possibly be based on natural kinds. So that's a second reason for proposing a new system. And a third one is that it offers us opportunities to explore fundamental questions. And I mean questions as fundamental as how does life emerge from a non-living world? Or how did life on Earth evolve over 4 billion years? Or are we alone in the cosmos? These are really big questions, but I don't think they're going to be answered without studying minerals that preserve that history. Minerals are the only objects we have that preserve billions of years of history. Okay, so we're proposing a different classification system. And here's the argument. The primary tangible evidence we have for any process in the solar system going back 4.5 billion years, even going back much farther than that, including the origin and evolution of life, it's information-rich rocks and minerals, these beautiful specimens in which each specimen is a time capsule. It's just waiting to be opened if we study it in the right way. So the key to understanding the coevolution of Earth and life, it's this emerging field of mineral evolution. And I want to take you on a journey now, and it's a 3-part journey that I've experienced over the last 15 years or so called mineral evolution. The first paper came out in 2008. It was started a couple of years before that. And this paper is what I consider part 1 of this story. It's the qualitative introduction of an idea of mineral evolution. So mineral evolution is the study of the changing diversity and the distribution of minerals as a consequence of evolving physical, chemical, and ultimately on Earth, biological processes. So what are we talking about when we talk about mineral evolution? We're talking about changes in a number of things. Just the diversity of mineral species, an increase in the number of different mineral kinds, the relative abundances of those minerals, the compositional range, and this includes things like trace and minor elements and even isotopes in those minerals. And also the morphology, the size and shapes that we all love. You know, most mineralogists, when they're talking about mineral species in the IMA sense, they don't really talk about morphology. But boy, that's so important, and it tells us something about the history. So these are all parts of mineral evolution. So far, we've focused exclusively on near surface processes, the upper 3 kilometers or so, because that's what we can study when we walk around the surface of Earth or go down in mines. It's what we're most likely to observe on other planets and moons, and it's where you get direct interaction of minerals with biology, and all these are really important in mineral evolution. And I have to take a sort of a pause here and make a comment about the word evolution. When we first came out with the mineral evolution paper, we had some pretty intense criticism, especially from biologists saying, oh, come on, you can't use the word evolution and talk about minerals in the same sentence. It just isn't, it isn't right. And it's, you know, biologists own the word evolution. Well, I disagree. There's been more than a century of publications in geology where we talk about evolution of igneous rocks and evolution of meteorites and evolution of planets and so forth. So it's used colloquially as just meaning change over time, but there's also an implication in an evolving system of complexification. We certainly see that with minerals, going from simple to greater complexity. Also, there's an implication of what's called congruency, that is each stage of mineral evolution follows from previous stages. It depends on the previous stages. You can't in and barrel before you have certain other minerals that are precursors to those. But it's not this. I want you to put this out of your mind. It's not Darwinian evolution. It's a different kind of evolution, but it certainly follows that. So here we have mineral evolution. The soundbite: new minerals formed through a combination of chemical, physical, and ultimately biological processes. Every one of these beautiful specimens has a story. It has a history. And the history that we've described involves 10 stages of mineral evolution that span 4.5 billion years. Now, there is a starting point that goes back much before that, many billions of years in some cases before our solar system existed. And those are minerals that formed around energetic stars, stars that were very old and shedding their atmospheres. And in those cooling atmospheres that were rich in elements like silicon and titanium and oxygen and carbon, you form tiny grains of about 20 different minerals. Those called the minerals. It's the 0th stage, if you will. All planets and moons form from those minerals. They have about a dozen different essential chemical elements, and you can argue that the mineral evolution story is basically asking, how do we get from 20 different minerals with roughly 12 essential elements to what we see today, which is much more than 5,700 minerals now, with 72 essential elements. That's the mineral evolution story. And we argue it took place in 10 stages, each of them sort of qualitatively a different time period. Primary chondrite minerals, these are the earliest condensates in the solar nebula as it cooled. So these things that basically are precipitated directly from a gas phase, about 90 different mineral species. The stage 2 is then you take all those chondrule minerals, they come together to form larger structures. They're affected by water alteration and thermal alteration and impacts that get you up to about 300 different mineral species. And stage 3, then you form larger bodies, the earliest planets. If the planets are dry, like Mercury or the moon, we think this is probably similar to the minerals that you find in meteorites. It's pretty much the end point of these worlds. They can't get past stage 3. If you have a wet planet, then you can form a whole bunch of additional things. If you have oceans or rain or something like that on the surface, you get hydroxides and clays and other water-bearing minerals. That gets you up about 450 mineral species. And we think that this is very close to the end point of Mars. So here we have stage 3. But Earth has a lot of other tricks up her sleeve. Stage 4 is the formation of granite. Granites form when you partially melt wet basalt or sediments, and you not only form a different kind of rock, much more rich in silica, but you have all sorts of glorious pegmatite minerals. Gets you up to about 1,000 different species in all. That's stage 4. And Earth then even has more processing of the crust and upper mantle through plate tectonics. We think this probably started in earnest about 3 billion years ago, and there were new modes of volcanism. There's all these massive base metal deposits which give us sulfide and sulfur salt minerals. It's the first time that you get a lot of mountain building with high pressure minerals brought to the surface through different kinds of erosion processes and tectonic processes. So lots of different minerals, and up to about 3,000 species then at the end of stage 5. Okay, deep breath. We've gone through 5 stages and produced about 3,000 different mineral species through purely chemical and physical processes. But on Earth today, we have more than 5,000. We have more than 5,700 known species. And how in the world is that possible? And the answer, amazingly, is life. Life has been a principal factor in the production of new minerals on Earth. This is intriguing to me because I was studying, these ideas all came to us when I was studying minerals and the origin of life. And minerals are said to play many roles. They're catalysts, they're reactants, they select molecules as templates, they protect those molecules, scaffolds to build larger structures. All these are roles of minerals in the origin of life, but in the same token, then minerals play a key role, life plays a key role in the origin of minerals. So this is a co-evolving geosphere and biosphere. Stage 6, the earliest life forms were tiny microbes that use the chemical energy of rocks to survive, but they really didn't produce a lot of new mineral species. The punctuation event was the great oxidation event about 2.5 to 2 billion years ago. putting oxygen into Earth's atmosphere caused the entire surface chemistry to change. And many of the favorite microminerals that I've collected in my life are minerals that formed as weathering products in a near surface environment. For example, in mining districts, thousands of new minerals, including most of the copper minerals. They simply won't form without oxygen in the atmosphere. That's true for 90% of the uranium minerals. These beautiful, colorful minerals just simply don't occur until you have oxygen freely available to react with previous minerals. And hundreds and hundreds of other minerals of what are called redox sensitive elements, minerals that have different oxidation states, and therefore you can change them when you oxidize those minerals. So that's the main source of mineral novelty over the last 2.5 billion years. There was a stage 8 where the oceans became more and more oxygenated, first at the surface and then deeper and deeper, until today the entire ocean from top to bottom is oxygenated. There is stage 9 where the principal mineral at Earth's surface, believe it or not, was ice, snowball Earth, where you had glaciation perhaps all the way down to close to the poles. So ice covered most of the globe. And then stage 10, the last of the 10 stages, is the Phanerozoic Biomineralization, where life plays a key role. This gets us up to 5,700 mineral species of all kinds. There are coal minerals, and there's minerals that form when cactuses and other forms rot. There are minerals that are precipitated by microbes, including the micromineral Hazenite, which only is known from Mono Lake in California, and so forth. So this is an amazing story. I have to share one story with you that's sort of an aside, but just to give you a sense of how amazing biomineralization can be. Trilobites have compound eyes. Every one of those little eye facets is a lens formed of a single calcite crystal, with the C-axis of the calcite pointing directly out at you. Amazing. But there's a problem. Calcite is a lousy lens material because red and blue light bend differently. It has chromatic aberration. But what does evolution do? You now have not pure calcite, but a little bit of magnesium enters that crystal lattice. And furthermore, the magnesium is radially zoned so that the calcium to magnesium ratio changes systematically from the center of the lens to the outside, and it exactly corrects for chromatic aberration. That's what evolution can do for you. It's a very amazing process in nano engineering, I've got to say. that's trilobite eyes, and that's biomineralization. So what did we learn from mineral evolution the first 2 years? Well, Earth's mineralogy is diversified dramatically. We see that there's a characteristic sequence of new mineral forming process, and each of those new processes explored a new pressure, temperature, and composition regime, and that the biosphere has been a major factor in the diversity and distribution of Earth's minerals. Those are qualitative discoveries that I think were significant. Also, for me, what has been really important is mineral evolution has represented a new framing of mineralogy. This is used in education and engagement. And we talked about this, some of us, earlier. When I was just a young boy, 10 years old, 12 years old, and into my teenage years, I'd go every month and visit the Old American Museum of Natural History, the Morgan Hall of Minerals, which is arranged by the Dana system. And it was case after case after case with native elements and sulfides and sulfur salts and so forth. And I studied those, but there wasn't really a story here. It was just a lot of beautiful specimens. Here's the new American Museum of Natural History, opened just last year. And part of the organization that George Harlow put together is the evolution of minerals. It's much more of a story. And I urge you all, when you get a chance to go to New York, visit the American Museum in this new museum. But it isn't just there. The Vienna Natural History Museum has a mineral evolution exhibit, the Paris Natural History Museum, and the recently opened Tucson Mineral Museum. The whole first half of the museum is mineral evolution. So this has become now a way of introducing non-specialists to the wonderful world of minerals and putting it in a narrative context, which I think is very powerful. Okay, so that's great, but it's a very qualitative story. It's a beautiful story, but there's not a lot of meat on the bones as a scientist. We need a more quantitative approach. And the way we've decided to do this is to harness deep time data and the power of data-driven discovery. So this is part 2. It took about a decade from 2010 to just a few years ago. And what we did was we built a database for mineral evolution. Here's Bob Downs and his great rough database. I'm sure many of you use this. It's the official list of IMA minerals. It's up to 5,780 species today. And you can type on that evolution icon, students Josh Golden and Alex Pyers, and an army of undergraduates to help build this. And we now have 200,000 mineral locality age data. You can look up your favorite mineral and see how it's distributed across time, as well as geographical, because it gives you mineral locality and age data. We focused a lot of attention on the first row of transition elements. These are familiar things like iron and cobalt and copper. They're very common in Earth's crust. They're economically important. They're sensitive to oxygen. Their chemical behavior is, and they play important roles in biology. So there's sort of natural things to study. And we tabulated these. And here's a plot that's it's a little tricky to see. The vertical scale is how many specific mineral locality occurrences there are, divided into 50 million year bins. This goes back 1 billion, 2 billion, 3 billion, 4 billion years. And it's also colored by the oxidation state of the mineral. So there's a lot of information buried in this one graph. Let me explain a little bit more. There's two main trends we see. The first has to do with what's called the supercontinent cycle. 5 times in Earth's past, all the continents have come together into a great continent. Here you're seeing an image of the most recent period when Pangea formed, and then the continent splits apart like it's doing today. The Atlantic Ocean is getting wider. And if you look at the history of minerals, particularly the very robust mineral zircon, that's a zirconium silicate that's so durable that it lasts through cycles of sedimentation. And it also has uranium, so we can get ages off them. And tens of thousands, hundreds of thousands of zircon grains have been dated. And if you look at all that accumulated data, what you'll find is that there's 5 spikes. And each of those spikes, it turns out, correlates with a period of supercontinent assembly. So what's happening is when supercontinents are assembling, you're building mountain ranges, you have lots of igneous activity, you're forming lots of minerals, and the zircons preserve those periods of formation. And we see the exact same thing in our pattern of the transition element minerals. Each billion-year period on this graph is the maximum form under one of those supercontinent cycle assemblies. So that's an important part. Supercontinents make minerals. The second thing has to do with the effects of oxygen. So think about copper. It can form in a native copper. You can have +1 minerals like cuprite. You can have +2 minerals like azurite and malachite. And so Shauna Morrison and Simone Runyon put together a huge database of copper minerals through time and then colored them according to whether they were +1 or +2 minerals. And what you see is there's this very strong increase in the average oxidation state of copper minerals, especially in the last 500 million years. So this is the kind of effect that we see. There's much, much more detail, but that's the sort of thing. We can make plots like the skyline diagram of all the first row transition elements where you have different elements on this scale. You have the numbers of occurrences and you have the age, and this is the kind of visualization we can do with the data that we have. We can do this for every chemical element. If you go on our website, you can find your favorite element and see exactly how the minerals of that element changed through time. We can also do some neat tricks with plate tectonic reconstructions with our colleagues at the University of Sydney who do the G-plates platform. We can model the changes of Earth's continents over the last actually billion years, and you'll see little yellow and black dots coming up. They represent copper and uranium mineralization, and virtually every new mineral deposit that we've plotted here occurs at a plate boundary. So we can understand the relationship between plate tectonics and mineralization. So what have we learned from this second phase of mineral evolution in the mineral evolution database? We see the episodicity in the age correlated with supercontinent assembly. And what I haven't told you about is that these different chemical elements reveal very interesting differences in the details of those 5 supercontinent assembly periods. We also see redox sensitive elements, including transition elements. They increase in their oxidation state through time. And what I haven't told you about is that we can also correlate the depths of formation of these minerals to understand more about crustal oxidation, which is something you can't get with other proxies so far. So these are all exciting new developments. And this is a quantitative approach, but I have to confess it doesn't fully exploit the potential of mineral data. And what do I mean by that? We're starting this evolutionary system because minerals have vastly more information than I've just talked about. And we're going to apply analytical and visualization methods to these growing data resources. So let me remind you about minerals. Every specimen, they're trace and minor elements, dozens of them in every specimen you have. Isotopes, hundreds of different isotopic systems to study. Structural defects, solid and fluid inclusions. There's all the morphological information, their size and shape, crystal form, physical properties, petrologic context, all this and more. These are information-rich systems. And so part 3 is mineral informatics. This is ongoing. It started in 2019. The first thing we need is data resources. I told you about RUF. You all know MinDat. It's an incredible resource, and Jolion's very much part of our team. Handbook of Mineralogy, Rock Forming Minerals, hundreds of thousands of original articles. All these data are things we need to add and build data resources. And they enable new analytical approaches. And I want to give you some eye candy now, because these are the things I love. This is something called a chord diagram, never been applied before to minerals, but these are the 30 most common cobalt minerals. They occur as arcs around the side here. There's 30 little arcs. And then you can see for each mineral like erythrite, what other minerals does it coexist with in a pairwise way? And you see there's some very, very strong connections, but there are other connections that are hardly anything at all. And there's so much information in a diagram like this. If you want to understand cobalt minerals and their deposits, this is a visual diagram that has huge amounts of information that can help us. Here's another kind. This is called a clay diagram. In this case, it's a 72 by 72 matrix in which each of those matrix elements says, if you have element number 1 in a mineral like cobalt, what's the possibility that arsenic will also coexist? And you know the crustal abundance of these elements. You can say, oh, there's a probability that you're going to have cobalt and arsenic coexist. But in some cases like this one, there's a hot spot that indicates, wow, there's a lot more cobalt arsenic minerals than you'd expect just by looking at crustal abundances. 5,000 matrix elements, every one of these could be a PhD thesis. This is a huge amount of information. And we're not even done with this. We can do this in 3 dimensions. This is a 30 by 30 by 30 clay diagram of the most abundant chemical elements in minerals. And each hot spot indicates if you have elements 1 and 2, what is the probability that you're going to see element 3 in that mineral? And so here we have 27,000 matrix cells. Again, every one of them is a separate story that you can analyze and think about. That's the power of data. One of our favorite things are network analyses. We started making networks back in 2016 with our colleagues at RPI. This is a very simple network, just 37 nodes, each one representing a different primary igneous mineral, as listed in Harker's Petrology for students. Harker's Petrology has about 100 different rocks, and every different rock type you've ever heard about for an igneous rock, there's granite, there's olivine basalt, there's nepheline cyanide. Every igneous rock is embedded in this diagram, and you can understand igneous petrology in a new way by looking at these network diagrams. We do this for minerals. For example, on the left, there's chromium minerals. On the right, copper minerals. These are what are called force-directed diagrams, which means you can interact with them. You can study the links between different kinds of minerals. You can color them. And the chromium minerals, orange, are all the igneous primary minerals. The big circle is chromite, by the way. Green are different minerals that form in soil as chromates. In the copper case, we've colored them by different compositions. So red are the sulfides, orange are the sulfates, blue are the oxides and silicates that don't contain sulfur. There's so much information in a diagram like this. You could study them for weeks and weeks and weeks and learn new things. We can do this in 3 dimensions. Here's Dan Hummer's work on manganese. You'll see this little bump at the top. Those are mostly divalent manganese. These are colored by oxidation state. So you're seeing a little cluster there of manganese phosphates that are in granites. You got another little cluster here of the higher pressure manganese metamorphic minerals. And then the big central part, literally, technically, it's called the hairball. that contains all the surface black and sometimes not so attractive manganese minerals. I love them all though. And this is something you can do also in 3 dimensions. You can play with this, you can rotate it. You can see how these different minerals are associated. You can zoom in on your favorite manganese mineral. And these are all interactive graphs that are available on our website. These and many other graphs that can give you a sense of how mineral network analysis can tell us about the coexistence of minerals. You can even do this in virtual reality. Here's my colleague, Shauna Morrison, looking at a network diagram of carbon minerals. In red are localities, and in blue are the different carbon-based minerals, and the localities are linked to the minerals, and you can see information. This is really fun. Okay, that was just an aside. I love this stuff, and as I say, it's sort of it's not only a way to learn, but there's also an aesthetic to it. So here's a key idea. We can exploit these large and growing mineral data resources to develop an evolutionary system of mineralogy. And that evolutionary system gives us insights about the coevolution of Earth and life. But to do this, we need a different classification system, and it differs from the IMA protocols in 3 ways. In some cases, we split IMA species into several different natural kinds. In other cases, lump a bunch of IMA species into a single natural kind. And we think amorphous materials, glasses, and so forth can be really important planetary history, so we include them, even though IMA seldom does. So let's just think about one mineral, diamond. And how can we say that there's more than one kind of diamond? Well, think about it. We have pre-solar diamonds. These are diamonds that formed more than 4.5 billion years ago in a high vacuum around a star, in the cooling, expanding envelopes of stars that are carbon rich. Those are different from type 1 diamonds, which form high pressure, high temperature, deep in Earth, at basically in an aqueous fluid that's saturated with carbon, which is different from type 2 diamonds. They've been in the news a lot lately. Type 2 diamonds are formed at high temperature and high pressure, but in a metallic fluid saturated with carbon. That's different from impact diamonds, and it's different from this weird stuff called carbonado. Some of you may have seen an auction recently of a 555 carat polished carbonado called Enigma. Well, that's different from any of these other kinds of diamonds, and there may be more, but there are at least 5 natural kinds. Same thing true for apatite. Meteoritic apatite forms in one way. The beautiful apatite you find in pegmatites is a different kind, and the apatite in your bones and teeth, I would argue, is a different natural kind. These just aren't the same thing. They may all be apatite in the IMA scheme, but not in ours. The single mineral that has the most natural kinds that we've identified so far is pyrite. We've found as many as 21 natural kinds of pyrite, some formed at high temperature, some at low temperature, some formed biotically, some formed abiotically, some formed with an aqueous fluid, and some formed with a sulfide fluid. These are just different formation environments. They lead to different kinds of pyrite. Now, in other cases, like the tourmaline group, we lump species. There are more than 30 IMA approved tourmaline species, but if you look at these beautiful crystals of elbite, actually you can have as many as 6 or 7 tourmaline species in a single crystal. And we would argue that that would just be one natural kind. We can see this at a microscopic scale, the work of Ed Grew on very ancient tourmaline crystals from Azua. They're only a few tenths of a millimeter across, and yet there's 2 species here, depending on the magnesium iron ratio. There's some schorl, there's some dravite. They're all just zoned across here. We think that's a single natural kind, not 2 species. And then finally, we include amorphous materials, the volcanic glass obsidian, coal, limonite, pyrolusite, other things that are amorphous or are nanophase materials. By the way, these were all included in Dana's 1850 system, but it was since the advent of X-ray diffraction. These don't diffract X-rays very well, so they're not considered by the IMA. But when we went to Mars in Curiosity rover, my colleagues and I on the Curiosity rover team have found that the sediments contain from 50 to 70% amorphous phases. If we're going to understand the origin of Mars and its current surface environment, we have to include amorphous phases. They're essential to understanding the history of a planet. So that's part of it. All of this has been systematized in a variety of papers, especially one that's coming out in July on the paragenetic mode of minerals, another one on lumping and splitting. What we have to do when we're doing these big data studies is create data objects. And these can take months and months and months. I spent 6 months of my COVID isolation building a database with 5,700 rows, each representing a different IMA species, and 57 columns, each representing a different way that minerals formed. And the blanks and the ones here say that, forsterite forms by a particular paragenetic mode or iron or so forth. So this is a way of systematizing all minerals and understanding how they formed, and it leads us to the evolutionary system. The easiest way to show an evolutionary system, this is a binomial nomenclature. You have the official IMA species name like graphite, and then you have a prefix, which is the type of formation environment. So a type 2 supernova and graphite, that's SN2 graphite. Here's moissanite, silicon carbide, formed in an AGB star. We can show these with beautiful network diagrams, bipartite network diagrams with 2 kinds of nodes. So here, for example, is a type 2 supernova. Here is the AGB star, shown with star-shaped icons. And then the diamond-shaped icons there's moissanite, there's graphite. Each mineral is connected to one or more kinds of stars. Each star is connected to one or more kinds of minerals. This gives us this beautiful diagram. And you're going to see more of these as we go through the evolutionary system. But I wanted to just take a break and talk about a kind of microminerals that you may not have ever experienced in your collection, because they actually typically are much less than a micron in diameter. This is cluster analysis, and here's how we get these distinctions between different kinds of minerals. We start with a meteorite, we dissolve it in acid, we extract these incredibly tiny grains of silicon carbide in this case. They're acid insoluble, so we can extract them. You can then build databases. Larry Nittler is one of my heroes. He's a nano-mineralogist. He mounts these incredibly tiny crystals and studies them, looks at their isotopic analyses. We have a database with 17,000 analyses of silicon carbide built by people at Chicago, University of Chicago, and the Washington University in St. Louis, and Carnegie Institution, my own institution. And you can plot the isotopic values of these, and they have different clusters. They're very distinct groups, and they represent different kinds of stars. And so that's how we do cluster analysis. Lots of papers coming out that analyzed with new kinds of clustering techniques, and I'm happy to send anybody interested papers that describe natural kind clustering. In this case, we've learned some really interesting things. These moissanite grains point to several distinct environments in AGB stars. By the way, our sun will become an AGB star in another few billion years, and it will form silicon carbide grains. And they will have different silicon and carbon and nitrogen, aluminum isotopes, and that will tell us something about that star. Other cluster analysis, we've seen there are multiple kinds of pyrite based on different trace element patterns, and we're building huge databases. I mean, hundreds of thousands of analyses for garnets and feldspars and other minerals. This is an ongoing beginning project, really exciting. So much more work to done. I should be working in the lab right now. Anyway, so part 2 of the system is interstellar and solar primary nebular minerals, and you start expanding that graph to include the solar nebula and including interstellar clouds and ices that form. So you see the network expands. This is the expansion of mineral evolution that you're seeing in graphical form. We go to part 3. These are the primary chondrite mineralogy. This is stage 1, if you will, because everything before that was stellar. And you see the expansion of the graph, and then we add aqueous alteration, impact alteration, and thermal alteration, and the graph gets larger and larger. Here we have about 300 different minerals that are known to occur in meteorites and still fall to Earth. We then can speculate on the earliest Hadean Earth, the period before we have any actual minerals preserved, but we can make good guesses. In green are new minerals that we think occurred on Earth, but not in meteorites. In red are minerals that occur in meteorites, but not on Earth. And in yellow are minerals that occurred both on Earth and in meteorites. By the way, there's the original stellar network. It's still buried in there. It has to be. That's the first part that I showed you. But as we move farther and farther along, this is going to be there. We think, by the way, that this is what Mars looks like. This is the network of minerals on Mars. It may be slightly different, but this is a hypothesis we have. And we're going to take a deep breath deep breath, because here now is the network of all 5,700 minerals linked to 57 different formation processes. The stellar minerals that are still in there somewhere. In green are biological minerals, in red are igneous minerals, in blue are aqueous minerals. There's all the different kinds of formation processes here. This is the first, to my knowledge, visualization of all mineralogy in a single graph. Every one of your favorite minerals is somewhere on this chart. Now, what have we learned? This is just the beginning, but we found that water is by far the principal driver of diversification. More than perhaps 90% of species on Earth form through fluid rock interactions or other kinds of aqueous processes. And this explains very simply why the moon and Mercury are so few minerals compared to Earth, 5,700 and counting. A second thing is biology does play a major role in mineral diversity. Life mediates about half of all known mineral species in one way or another, and more than a third of the known mineral species are only known to form through biological processes. So life is really a big player in this. Here's one of the most interesting things, and I think for people interested in microminerals, this is really profound. Okay, 42% of minerals, not quite half, but a lot of minerals require one or more of 41 incredibly rare chemical elements, things like the rare earth elements in the platinum group and arsenic and molybdenum, tin, others. Now, those 41 rare chemical elements, get this, those 41 chemical elements collectively represent only 1 out of every 10,000 crustal atoms. These are rare elements, and yet they are necessary, they are essential for 42% of all the mineral species. That's going on 2,500 species that absolutely demand one of these rare elements. I think that's amazing, and it shows you how these rare elements add so much to our mineral diversity. And it only happens because of fluid rock interaction, because it's only with fluid rock interaction that you can concentrate and select those elements. And finally, this is a hypothesis, but one that we're exploring very, very deeply. We think that the diversity and distribution of minerals on Earth, as represented by this network diagram, is a planetary scale biosignature. That is, this diagram and the metrics associated with this network tell us something about life. So that's something we're exploring. We're really excited about it. My conclusion, we've entered this new age of mineral informatics. We're here, it's on us, and it's so exciting. You can use multidimensional analysis, you can use all these visualization techniques, because every mineral is a time capsule. It's so rich in information, and we're learning about the insights of the coevolution of Earth and life as a result. Thank you so much for the opportunity to share this with you. I'm just going to put this slide up with my funding agencies, and I hope that there is time for questions. I really enjoy having a chance to talk to you about this stuff.